Now we're going to look at the Goldman-Hodgkin-Katz equation. We've managed to survive the Nernst equation and get through that without too much damage to our psyches. And so I want to try out one more algebraic equation, which, like the Nernst equation, looks really difficult at first. But when we look at the concepts that underlie it and the way that we can simplify it, like the Nernst equation, it's not going to be so bad. So let's get started on that. So here's the Goldman-Hodgkin-Katz equation. There's different versions of this. Some textbooks will have the Goldman equation. This is the Goldman-Hodgkin-Katz version, and it's the one that I prefer to use. And what it does is describe how the membrane voltage is dependent on the conductance of each ion multiplied by the equilibrium potential of each ion. So here's the conductance for sodium. Here's the conductance for potassium. Here's the conductance for chloride. What do I mean by conductance? Well, that's the same thing as permeability, but where charges are moving, and all of these are charged. Sodium ions have a positive charge. Potassium ions have a positive charge. Chloride ions have a negative charge, and so these are charges moving across the membrane. So in electrical terms, we talk about conductance rather than permeability, but this is closely related to the permeability for sodium, for potassium, and for chloride. So we take the average, basically, of all the different conductances times the equilibrium potential. In the denominator on the bottom of this equation is GNA plus GK plus GCl, which is the total conductance for all three of these ions. We can expand this out to all the ions that are in the human body, but we don't really need to do that. We're just going to consider sodium and potassium. We're not even going to consider chloride, and I'm going to show you how that simplifies this analysis by quite a bit. Here we are looking at the Goldman-Hodgkin-Katz equation again. And so what happens if only sodium ion channels are present and able to open? Then only sodium can flow across the cell membrane. The only conductance is that of sodium. What happens if only potassium ion channels are present and open? Then only potassium can move across the cell membrane. What happens if only chloride ion channels are present and open? Then only chloride can move across the cell membrane, and so the only non-zero conductance is that for chloride. So let's use those ideas to simplify our analysis of this equation. I'm just going to do GK. I'm going to do the conductance for potassium and look at just potassium. But I think you'll be able to see how easily this resolves for looking at sodium and for looking at chloride. I'm going to leave that up to you to do that work. So what happens if only potassium ions are able to cross the neuronal membrane through potassium channels? Well, in that case, sodium by definition can't cross, and that makes the conductance of sodium zero. And it doesn't matter what the equilibrium potential for sodium is. Anything times zero is still zero, so that term cancels out. The chloride conductance is similarly zero. There's no conductance for chloride, and so that number times ECl is zero. So that's a zero too. So in the numerator at the top of this, we're left with GK times EK. Now in the denominator on the bottom, we have GNA of zero because there's no sodium conductance. Potassium is the only thing that can move, and there's no chloride conductance. So now if you look at this, it resolves to GK EK over GK. So the voltage on the membrane, V sub M, is equal to GK EK over GK. GK over GK is 1, and so this says that the membrane voltage goes to EK. That makes perfect sense given what we were looking at before, because remember that the equilibrium potential is the balance between the electrical force and the diffusional force. And when those two forces are equal and opposite, then we say that they're in equilibrium. Another way of looking at that is for every potassium ion that comes in, a potassium ion goes out, and so it stays at that equilibrium. And it makes sense that if the only thing that can move is potassium, that potassium reaches the potassium equilibrium, and so therefore the voltage on the membrane reaches the potassium equilibrium potential. So Vm equals Ek. That's what this simplifies to, and we're going to use that simplifying assumption as we look at the analysis of the resting potential and the analysis of the action potential that are coming up in the next two objectives.